In this next module, we're going to discuss routing layer 3 to external networks. So to begin with, we'll take a look at an overview of why do we need to integrate layer 3 routing to the outside of the ACI. Should be pretty self-explanatory. That'll be a fast part. We'll go into some configuration for L3, just the basics of layer 3 external routing. And then we'll talk about transit routing, the requirements, and look at the configuration and a lot of sample. Now this will all be done so far currently in the slide-based modules, but we will also be taking a look at this later on in the actual hands-on demonstration as well. And we'll talk about some design considerations. So to begin with, an overview of the need for layer 3 routing outside of ACI. It's not too hard to understand that we're going to need to have our subnets that we create inside of ACI propagated or advertised outside of the fabric for the rest of our enterprise network, for outside of our data center to our MPLS, to our other headquarter or branch offices, to carriers for various reasons, L3 MPLS, I think I said that, whatever other needs that we might have for routing. There's really a lot of different situations where we might need to provide routing. Might even be to something as simple as a L4 through 7 device, like an ASA or a firewall or a load balancer of some sort. So a lot of different reasons. We may even be talking directly to a host, like a Linux machine or an AS400. There's a lot of reasons we'll need to provide layer 3 routing. Now keep in mind that the layer 3 routing goes from the private network or the VRF. And remember that for every tenant and private network, this creates a VRF. So if we have 2 private networks within a tenant, this is 2 VRFs. If we have, let's say, 2 different tenants and each only has 1 private network, this is also still 2 VRFs. So if we take a look at our connection to our external L3, we can see that from the tenant view, and of course L3 routing, just like L2 bridging, is done from the virtual, the overlay, which is the tenant. So from the left navigation tenant side, we see networking, and we already took a look at our external bridge networks. Now we're looking at our external routed networks. And we can see, we'll talk a little bit later about action rule profiles, but we can see that we have multiple L3 outs configured for this particular tenant. So we have one L3 out 1, and the second is L3 out -2. And we can actually see from this view that they are a part of 2 different contexts, or 2 different private networks, or 2 different VRFs. So all the same thing. Whether we say, or whether you see in, let's say, the managed object model, it's called a CTX or a context. And actually this goes along with the way that we label VRFs in Nexus or NXOS in standalone mode or 7K, 5K, 6K. They are called VRF context and then the name. So it kind of goes along with that quite well. Private network, a little bit of a different naming. VRF, that's what we're used to. And do keep in mind that the VRF, this is going to become important when you're looking at your routing table or your RIB, for a particular VRF. First of all, everything is in a VRF. There's no routing in the default global table. And so every VRF is going to be a concatenation of the tenant name and then the private network name. So again, we can see L3 out 1 is a member of, or using, member of context 1, which is a private network, and L3 out 2 is a member of private network named network-2. And so here we can see that from one L3 out, we are going to create 1 or multiple networks, and these create EPGs. Now, essentially what these are is subnets, and we'll take a deeper look at this later. But we have the ability to identify individual subnets or multiple individual subnets and classify those as an EPG. And then we could classify the rest of the subnets or additional subnets, or even a 0000 kind of aggregate route as a separate EPG. And what this allows us is to have separate contracts or ACLs, as well as to instantiate different L4 through 7 services when we begin talking about those from the outside world, from particular subnets to the inside EPGs. So for instance, I could have one contract from everyone, 0000, to a web tier that only allows port 80 and 443 and redirects me first to a firewall and then to a load balancer. And then I could have another subnet for, let's say, my developers, and that's a specific subnet, specific prefix. It's a longer match or longest match, and it has a contract that can get to the web tier, the app tier, and the database tier, all on port 22 for SSH. So these are the kinds of granular configurations that we can do based on or by creating multiple EPGs based on their subnet prefix. So taking a look at the configuration for L3, we can see that when we are in our tenant and when we've created or right-clicked and said create new routed outside, we have multiple options. First of all, we have to choose the node or the switch node, and then we choose the interface. And when we're choosing the interface, we can specify, actually when we choose the node, we choose what routing protocol, OSPF, EIGRP. Actually, this slide is, I forgot to update this particular slide. This says that only IBGP and OSPF v2 are supported, and that was initially true. So if you are working on an older version of ACI, 1.03 or 1.04 for instance, you will only have those two options, IBGP or OSPF v2 for IPv4. Currently, and has been for some time now, we do support EIGRP, OSPF v3, so we have full stack support for IPv6, and we also support eBGP now as well. And we also support something that you may have heard of in the past, or you may read documentation that is older that says that ACI does not support transit routing, meaning we learn prefixes from one router on one leaf and advertise those out to another router on either the same leaf or another leaf. And that was true in ACI 103 or 104 or older versions. Currently, and for some time now, we do support transit routing. And we'll actually go, as we took a look in the agenda, we'll go into those details. So with any choice of whatever routing protocol, and we also support static routes, of course, as well. Whatever routing protocol or static route we want to do, we have a choice of, do we want to create a routed interface, the equivalent of no switch port, an SVI, so switch port mode trunk, and we're trunking a particular transit VLAN, and we're doing adjacency or peering from SVI to SVI, or do we want a routed sub-interface? So using a .1q VLAN header, but still having a routed interface on that physical interface once we create the sub-interface and tag the .1q VLAN. So one of the things we want to take a look at is how packets forward from inside and outside the fabric. So first of all, we've already kind of taken a look at what happens kind of 2B over here. If we look at if the destination IP address was inside the tenant space, then ACI is going to forward, so from the inside to the inside, it's going to forward it to the tunnel endpoint where the destination endpoint is attached and learned. But if the destination was outside the fabric, then ACI will forward it to the TEP that's nearest to the external router, and it's going to use the best route or longest match if multiple external routes are attached. So routes learned from peering are marked as outside. With this, we see that we have a single data plane with essentially what we're calling two control planes. So which forwarding space is used to forward the packet is determined by which IP network it's in and where it's going. Okay, so again, this has to do with creating multiple EPGs and having multiple different potential contracts. So the inside networks are those associated with the tenants and their bridge domains. The outside networks are those associated with the outside routes for each of those tenants. Now, in order to get traffic into one leaf, and keep in mind, we are not running OSPF or EIGRP or IBG, well, actually we are, eBGP or anything like that inside the ACI fabric. So because we're not running, let's say, a standard routing protocol, BGP not really being a routing protocol, but really an application running over a routed protocol. Because we're not running OSPF or EIGRP between the leafs, then in order to get routes from one particular leaf to another leaf, and specifically to preserve tenant information, or really VRF information, more importantly and more specifically, we need to have some sort of overlay. So remember that the fabric itself is running IS to IS, right? Intermediate system to intermediate system, all on level 1, and this is allowing all of the loopbacks and all of the essentially the tunnel endpoint IPs to be learned inside the fabric. And again, this is just for the infrastructure, or the VRF that's actually named the VRF, if you hate the word VRF, that's actually named overlay-1. Okay, everything else is being sent through VXLAN, and if we happen to learn routes from the outside, we need some way of identifying the ingress leaf, really specifically the ingress VRF that it came in on, and propagating those out to, first of all, only the other leafs that have that VRF running. So if a endpoint was never learned in this particular, let's say leaf 1 for, let's say VRF, let's call it tenant 1, and maybe we have tenant 8 here, but we don't have tenant 1. Tenant 1 is over on, as we see here, let's say leaf 6 and leaf 5 and 4. Well, then 1, 2, and 3 would never have those VRFs instantiated to preserve address space, to preserve resources, processor, CPU, memory, stuff like that. So we are only going to instantiate the VRF and or bridge domains where we have endpoints attached for that particular tenant EPG bridge domain VRF. So that's the first thing. The second thing is we are going to run multi-protocol BGP. So if you're unfamiliar with multi-protocol BGP as opposed to just BGP, we are making use of two key items here, two key topics. And those are, in fact, let's just switch over to our whiteboard here real quick. With MP BGP, or multi-protocol BGP, we are using subsequent address family indicators in order to carry information. So we have things like the IPv4 and the IPv6 SAFI, or sub-address families, or subsequent address families as they're properly called. And we also have Multicast as well as another family. And essentially what's happening is we have two types of separation of routes. So first of all, if I have two different VRFs, let's say VRF1 and VRF2, I might have overlapping address space. And of course, the fabric itself, which is VRF overlay-1, also has, overlapping IP address space. So I might have different tenants that have different or overlapping IP address, and if I have those routes on the same leaf, well, that's fine, but I need a way to carry information back and forth between leafs and preserve that. Well, if we are inside the fabric, then all of that is handled through the APIC controller, and essentially sending the same distributed gateway through, maybe .1, through the SVIs, or propagating them, creating them on the, instantiating them really is the word I'm looking for, on the leaf switches in the proper VRF. The APIC controls all of that. But now let's say that, I'll just hide this layer. Now let's say that I have, for instance, two spines, and let's just keep it simple, and I have two leafs. And on these leafs, 101 and 102, I've got external routers. and let's just call it a point-to-point routed link. And let's say I have the 10.1.1.0/24 prefix and 10.1.1.0/24. And these are actually coming in through these point-to-point links to different tenants. So let's say that this one is coming into VRF tenant 1, and this one is coming into VRF tenant 2. So we need to get, and let's say we do have tenant 2 hosts over here off leaf 1, and we also have tenant 1 hosts. So I'll just use by the coloring. Tenant 1 hosts over here off of leaf 2. So we need to get the information we learn here over here, and we also need to get the information that we learn here, ingress prefixes, over to leaf 101 in the proper VRF. So what we're going to use is with multi-protocol, actually I meant to choose a different color there. With multi-protocol BGP, we're going to use something called a route distinguisher, which will keep our IP addresses isolated in the data plane, and then, or actually in the routing table, the database, and then we'll use something called route target, import export, and this is basically a value typically indicated by ASN colon VNI or VNID for the VXLAN VNID, but really it could be any value. It could be 1:1 for, let's say, VRF1, and it could be 2:2 for the tenant 2 VRF. So it really just depends. In the case of ACI, it's going to be all automatic. So it's going to choose for you. But essentially what's going to happen is these values are passed as BGP extended community values. And these indicate which VRF, when the traffic gets from one BGP peer to another, which VRF should that traffic be placed into? So let's say we learn a prefix here, and this prefix is, I'll go back to my color scheme, is actually a part of T2. So it gets brought in, and it needs to be sent over to the T2 VRF and inserted there into that rib so that the host can actually reach it. So then, likewise, let's say we learn about the prefix 10.1.1.0, which is overlapping through tenant 1. So that gets brought in and sent over multi-protocol BGP. Really, it doesn't go through both spines, so forgive the erroneous traffic flow. And it gets put into the T1 VRF here on leaf 102 so that traffic can get back and forth between the host that's a part of T1. So this is going along with the routes as a BGP extended community, and that's what allows us to separate out or indicate to the receiving BGP peer what VRF it should be a part of. But while it's in flow and even while it's in the database, the route distinguisher is a separate value also automatically created by ACI. And even in Nexus 9K standalone, the RT and RD values can be automated as well, with or without EVPN as a new subaddress family. But the route distinguisher provides a prefix that keeps these values separate. So again, it could be some sort of value, colon, and then, so let's call it value 1 for T1, and then value 2, colon, the IP address, to keep these separate in the BGP table. So that's just a brief kind of overview of MPBGP. It certainly does not go into any details there, or not many. But the fabric leverages multi-BGP for distributing these external routes to the leaf switches. In terms of creating our route reflectors, and actually I didn't kind of mention that, in terms of allowing for scalability, we use BGP route reflectors because as a rule of iBGP, all iBGP peers in an autonomous system have to be fully meshed, unless we either use confederations, pretty old, or BGP route reflectors. So typically we'll take 2 or possibly 3 or 4 of our spines, normally we have 2 spines, and we'll turn those on as BGP route reflectors. And normally this would be something that you would configure with the BGP route reflector client command on the actual route reflector under the peering, the neighbor command or the template that you're going to apply for your client or neighbor switches. However, in ACI it's much easier. So in ACI we simply click on Fabric, Fabric Policies, Pod Policies. So notice this is not access policies, this is fabric-wide. Pod policies and the BGP route reflector default. We give it an autonomous system number, something that if we're going to use iBGP or eBGP to peer from our fabric outside, if it's iBGP, it's something that either already exists or something that's not going to overlap with something else we have. If it's eBGP, something that is different than what we have outside. Okay, so we're going to give it an ASN and we're going to choose our route reflector nodes. Very simple. And then we take and we apply that to the second here, which is the the pod policy group, and we apply that default route reflector policy. And that's it. Multi-protocol BGP is set up for you. You don't have to do anything with RDs, RTs, creating your VRFs under your BGP, router BGP, specifying your IPv4, IPv6, multicast address families, all of it's automatically done. So then when we actually go to configure our BGP, or actually our external route peering, we're going to see that we have, for instance here, we're using a routed sub-interface, and currently the configuration that you see here on the external router is using the fact that in ACI 102, 103, 104, the ACI fabric had to be OSPF or iBGP, and if it was OSPF, it had to be a not so stubby area. So these are our LSA type 7s, right? So most likely this is going to be an ABR, our area border router, and it's going to do the translation between type 7 to type 5 conversions. Now the idea of a not so stubby area is that with a not so stubby area, we could be learning prefixes from really from another external router on this entire fabric, which is our NSSA, and redistributing those into OSPF, and then those would get turned from type 7 to type 5 and get sent back into at the area border router and get sent back into the rest of the area 0, right? So the rest of the OSPF domain. So that's one of the nice things about NSSA, but we can also do route summarization. Now, of course, the advertising router isn't always the forwarding router, but that's getting pretty deep into OSPF. So just to keep it simple, ACI 102 and 103 and 104 all had to be NSSA. So after this, in ACI 1.1 that we have now and all subsequent versions, our fabric can be OSPF area 0, it can be a backbone area, it can be a transit area. There's really no limitation to what we can do anymore. Really full OSPF v2 and v3 support is there. So that's just the configuration that you see here on this external router. Okay. So now with route redistribution, and again, some of these slides are older, we're going to go over the transit route slides as well. But for instance here, we have a external router with OSPF NSSA area, and this is redistributing from inside the ACI fabric. We have VMs, or bare metal hosts, that are a part of a VRF and a part of a subnet, or really, sorry, a part of a bridge domain that have a subnet, and one of the subnets is marked as public, and one of them is marked as private. Now, subnets that have the public flag or tick box, those will get advertised outside the fabric. So for instance, we will automatically redistribute into MPBGP and then from MPBGP into OSPF, the 100.110. And all that we had to do was tick the box on the subnet for public, and then also have a contract between whatever EPG has this subnet. Of course, the bridge domain has to have an associated L3 out, and this has to be the associated L3 out. And we'll take a look at this in the demonstration. As well as it has to have a contract between that EPG and the L3 out, or one of the network EPGs on the L3 out. So as long as that's the case, this subnet will get redistributed. So it doesn't just necessarily, because we tick the box for public, get redistributed everywhere. It's only per where we have the associated L3 out to the bridge domain and where we have a contract. So we do have a very tight ability to control where these subnets are advertised. We'll also learn about the 200.110/24 and the essentially router that is the leaf node. We'll redistribute that from OSPF into MPBGP, send it to the route reflector, which will send that down to any other leaf switch that has that VRF, and will receive and insert that route. So as I mentioned, prior to ACI 1.1, we had stub networks only. Okay, so the ACI was this stub network, and it could not do route redistribution. At the time, it was not designed initially for use as a transit node or to carry transit traffic. So at the time, the border leaf would only announce public subnets, and it automatically would create the route redistribution policy. So it would actually create a IP prefix list and a route map, of course, calling that prefix list in order to advertise the public subnets out. But at the time, the border leaf did not announce transit routes. So essentially, if you're working on a ACI 1.0 anything version, and you are learning, let's say, the 200.210/24 prefix via OSPF or IBGP at the time, then, and over here, you're learning from the right, you're learning the 200.110/24, then we're not going to advertise the 200.110 prefix, but we would advertise that internal public, so the 100.110/24. And likewise, over on the other side, we would still advertise the 100.110/24 public. We would not advertise the learnt 200.210. Now, of course, that was all prior to ACI 1.1. So now all of that is supported, and of course, we'll go over that configuration. So one of the things to consider when we're doing IBGP peering, as opposed to OSPF, is that essentially there's one AS number for the entire fabric, and so inside the fabric it's all IBGP, and then the customer edge router would have to have that same ASN for BGP in order to do IBGP peering. So we would have VRF Lite for tenant L3 separation and one IBGP peering per tenant. Again, this is all ACI 1.0. Now, still, even in ACI 1.1 and later versions, well, actually as of ACI 1.1, later versions may support larger. But if we have a large routing table, and we'll define the scope limits or verified scalability limits in a moment, and with the 9300 series leafs, we can't support the whole table. So if we need greater VRF support or sophisticated WAN features and sophisticated BGP policy, we may still need and probably will still use external customer edge routers, ASR 1000 or quite possibly ASR 9Ks. It's depending on the size of the customer. So taking a look at packet forwarding and fabric forwarding, we've already taken a look at the local station and global station tables. Now we're going to introduce a new station table on a leaf switch, which is the LPM, or longest prefix match table. So when we're doing an L3 outside connection, the external EPG is going to be derived based on the subnet. And of course, we have support for multiple subnets, and we might want different policies for different subnets or different external EPGs. So we have the ability to define, let's say, for instance, 100.110/24 and 100.120/24 as EPG1, external EPG1. And let's say two different prefixes, 200.110 and 200.120 as a second external EPG. And so those would go into the external LPM table here on leaf 6. And then on our external LPM table on leaf 1, we would see the various subnets that we might have learned from those external routers or external prefixes. So we're going to derive the source EPG and set the source EPG in the VXLAN header, of course. The external LPM table lookup will be done based on the destination IP, and we'll find the border leaf VTEP, so in this case leaf 6 for both prefixes. And then we'll derive the destination EPG by checking the destination IP in the LPM table of the egress VTEP leaf. And we'll apply policy based on the source destination EPG in the configured contract. So let's take a look at external. So that was from inside or internal EPGs to external. Now let's take a look at from external EPGs to the internal EPGs. So for this, the external EPG again is going to be derived from the subnet. We're going to check the source against the LPM table, and we'll derive the source EPG and mark it in the VXLAN header. And then the destination will be checked against the global station table. And again, we'll send this to the egress leaf. If there's a miss, we'll send it to the spine for proxy service lookup. And then at the egress, we'll try to apply policy at the ingress if there is a hit in the GST, but if there's a miss, we'll apply policy at the egress leaf. So one of the things to consider is ACI L3 outside for IP multicast traffic. So this actually kind of goes back to our layer 2 external as well. We talked about possibly having two different VLANs outside the fabric sort of merged into a single, or bridged into a single VXLAN bridge domain inside the ACI fabric. And the number one reason why I see people doing this, customers doing this in the field, is because today, even in ACI 1.1, ACI doesn't support PIM routing yet. That is, I think, slated for the next release. But currently, a lot of customers are wanting to migrate fully over to ACI, and they're not going to leave any legacy switches in their network. They might have routers, but they don't necessarily want to route all multicast traffic outside the fabric just to have it come back in so that it can go between two layer 2 bridge domains, in this case VXLAN. So what a lot of customers will do is they'll merge two different external VLANs into a single bridge domain, and then ACI certainly supports IGMP snooping and an IGMP snooping querier. And with the IGMP snooping querier, just like in all other traditional NXOS switches like the 7K, 5K, 6K, etc., if we create this snooping querier, then the fabric can go ahead, or really any switch can go ahead and bridge L2 multicast traffic and still have IGMP joins, really IGMP reports with a join, allow the proper ports to join in without flooding it everywhere, and not have to have PIM sparse mode. Now, of course, if we are doing or want to have PIM routing, or we need to go between layer 2 bridge domains, in this case VXLAN, then we have a need for an external PIM router. Either way works. So I've done either way. You do have to keep in mind with external L2, you want to be careful. You want to configure the miscabled protocol just in case you ever have a loop. It will shut down one of the links and still leave the other link forwarding for L2. But in a properly configured network, you shouldn't even have this, and you should be able to forward with both, probably a VPC link, so a port channel. But you should be able to have both two VLANs external to the fabric, merged or bridged inside the fabric in a single VXLAN bridge domain. And multicast works just fine with no PIM routing. And we'll demonstrate this in the demonstration portion as well. So you also can have PIM running on external PIM routers. So these could be your existing Cat6Ks or N6Ks or N7Ks or whatever you might have. So for instance, if I have two endpoints in the same EPG, IGMP snooping will be fine, of course. If I have them in two different EPGs, typically because of two different VLANs that I'm bringing into the fabric initially during migration, but in the same bridge domain, it's fine. But if I need to have traffic go between two bridge domains, then it has to go to an outside PIM router and route back in. So now let's take a look at layer 3 out or external configuration. So again, from within our tenant, we're going to click on or right-click on, actually expand networking, and then right-click on our external routed network and create a routed outside. We'll choose the routing protocol, and again, now we have BGP, OSPF, and EIGRP. You don't have to choose a protocol for static, it's just static. We'll choose our OSPF area ID. If it's BGP, we'll choose E or IBGP. We'll choose the VRF that this is going to be an extension of. And then we'll create what are called node profiles and interface profiles. So a node profile is the leaf switch. And then, of course, our interface profile comes, this is under the logical node profile. That's our leaf. And then as a subset of that, we create the interface profile, which is the actual VPC or just regular port channel, typically for layer 2 with SVI peering, or our routed interface, or our sub-routed or our routed sub-interface. And then we see our newly created external L3 out, and we do need to create a contract between it. And for instance here, the web contract is being provided by the web server farm and consumed by the external users. So we're going to activate really the steps to configure L3 is to activate the internal fabric route redistribution or MPBGP, to configure route peering, and then to define which internal network should be advertised to the outside and via which routing peers, and then to define those external subnets or EPGs and define the contracts and provide and consume those.